right here we got, kind of a gently sloping landscape. And this landscape is about 14,500 years old here. So how many people believe in global warming? Raise your hands. How many don't think it's not all that cracked up to be? Raise your hands. So anyway, if we'd had no global warming, the last 14,500 years ago, this would be several hundred feet of ice right here. You'd have to go over to where that tower is over there. There hasn't been any ice there for a couple 100,000 years. But if you go west, on the other side of the Vermilion River, the ice has been there was about 12,500 years ago. So if you're a believer in global warming or not, the polar bears are probably here 14,000 years ago. And then you can see our landscape is fairly level. And right here, if you look in the pit, you can see that there's kind of a break down there at around 3 feet. We got the black soil, the brown soil, we got the white soil, and then we got something down below there. So why everybody get down in the pit, we'll kind of talk about the soil. So I'll do a little bit of agronomy stuff here, but I'm going to talk about a little other stuff that's not agronomy too. Now come down the pit and have a good time. So you see, if you look at when they put the oats in, I don't think they tilled very deep, and everything is really loose, granular structure. It's a nice structure. I don't think they tilled this deep, but if you look down below, this would be the A horizon through here. But down the lower part, if you look at that, it's pretty dang hard. So the water's not going to soak through too good. You can see it when it breaks into kind of blocks. And so there's, when they've been farming it in the last few years, it's been too wet when they're farming it and they packed it down. What I kind of recommend is if a person wants to rip their soil, the time to rip it is when it's dry. So you could get some really good benefits from ripping when it's dry, and then the freezing and thawing this winter will help it out too. When you get down lower in the soil though, like down, this would be the BW horizon. Then the dominant soil structure would be a prismatic structure where it's more long up and down than wide. If you look at this, really, that's pretty natural. There's no real compaction in the soil there. So the only part I'd be concerned about the compaction is probably from here to here. How many people got any experience with ripping? Has it been successful for them, or?
Yes, but it was in the east.
What's that?
It was in the east, in the eastern corn belt.
Oh, okay. So if you did it when it was wet, all it would do is smear it. But if you do it when it's dry, it's going to fracture it all over, and it'll improve it. And then the winter freezing and thawing, hopefully that will improve it even more. So this is the BW horizon. So far we've looked at the AP horizon, the BW. And so here we got some white spots in the soil. We'll look at those. So here we got, this is hydrochloric acid. So we had no fizz there. We move down to here on those white spots and it fizzes all over. There's probably like 25% of the soil. Do that one more time for you here, how's that? About 25% of the soil is calcium carbonate. We move down here, there's even more, maybe 35%. And we'll move down there and it's less, maybe 10 to 15% of the soil is calcium carbonate. So there's a bulge of calcium carbonate from here to there. And what I like to have people do is look at soil as being a history book. So we got a history book up here, we got a history book down there, and they're both different. So this history book tells you that over the last 14,000 years or whatever, thousands of years ago, the water soaks into the soil about here to here until the native crop plants, the big blue stem, the Indian, and switchgrass, take the water back out by transpiration. Very little water is lost by evaporation from the soil surface. Later on we're going to talk about that more extensively, but you don't want evaporation from the surface.
Basically what I've got in here is just plain soil, and I've got some just plain water here and a filter, and basically putting water on the thing, and we're getting a nice basically clear water, filtered clear water going through that soil. And And I've got it pretty well wetted down here now, but what I'm going to do is I'm going to put a sodium or a salt, basically salty water here on it, and we're going to change that soil to try and get that a little bit more salty, but it's still coming out pretty clear. And so we'll let that kind of saturate in there, and we'll see what happens here. I'm going to go back now. Now we've got kind of a salty soil, should be.
Sodic, actually.
It's sodic. It's sodium sodium metaphosphate. There is what I put in there. It's just a solution of sodium. So, and there is a difference, you know, sodic, saline, and there's some chemical things, but we're going to kind of do the same. I'm going to now put a little rainwater on this thing and see if we can, and it starts coming down a little bit more brown. And basically what happened is we put that salt on there, and that salt, just in that short period of time, latched on to the clay particles, which are negative. We put a strong positive charge on there, and it's knocking off things like calcium, organic matter, knocking it off that cell, or those soil particles. And so you can see what happens from that salt, and it knocks it off. Well, the whole thing is that one of the discussion coming out of this whole deal then is we're tiling these areas. So the whole idea is to keep that water table down so it doesn't come up and bring that salt up and then evaporate on top, and then we start getting these sodic soils. And so by tiling that, then we keep it down in there. There's some discussion, though, that we brought that salt up, it knocked off the good things we like, calcium, organic matter, and so when it rains, then it takes it down, and it's taking it down into that soil. But usually then the salt that water made its way brought back up and brought up those things again, and then the salt stayed there and it took it down. Well, if you put the tile in, we're not bringing that water up. There's some concern that we're taking good things out of that every time it rains. Then we keep taking those things out until that salt is out of there. It's going to take it down. As far as consultants and people, then do we have to think about maybe some fertility things that we have to do to replace that out there? We typically then would go to gypsum, try to get some back and keep that pH up, and so we have to think of that. The other thing that I can't scientifically say, but there's some thought that if we take all these fine particles, these calciums and things down, would they ever get into a layer down there on top of that tile or before the tile that basically plugs up the soil? So there's some question. Then what we did is that by putting the tile in, we kind of were taking down these the fertility or the quality of the soil. And now if we clog it up, it's going to go down there and not drain either. So if it keeps raining, it just kind of stays there. So it could be a kind of a double whammy thing going on down in there. And I think as time goes on some of these soils, there's been a lot of tiling done down in South Dakota, and on these types of soils here that you can see right out here, you can tell it's saline out there just because of what's growing. Are we now going to have to kind of accept some new management practices and do some new things to amend that soil? And so it's kind of an interesting thing, and it's just basic chemistry. It just replaces those things and takes them down. the other topic I was going to talk about a little bit today as consultants and as agronomists, we're out, and as producers, we're taking a look at these fields, and we're starting to rely on some real precision ag things. We've got some really good maps, soil maps we're going on, and we've got the mapping going on from the yields maps, and it's a perfect time down in this part of the world to start looking at your own mapping just with the eyeball. You can look out there and start seeing how some of these soils change across the field. I think the most dramatic one I saw is I had to get some pictures for a magazine. They wanted to know, okay, when we rate a drought crop or a drought stressed crop, we call it excellent or very good and fair and poor and very poor. And so they wanted to know, well, what does that look like? How do you rate that? So I took a drive out of Sioux Falls and just came a little bit south. If anybody's over in here, the Schmenk farms are over northeast of here, just south of Sioux Falls. And I found a field there of corn that was what I would rate excellent. And this is not even 2 weeks ago now. There was excellent looking corn sitting there. But right next to it in that field, I took another picture of what I would call good. It looked good. And in there in that field, all of a sudden you could see these soils change, and then it was, it was fair. I got into one part of that field that went all the way down to very poor. It's gone. It's done. So in one field you could see that soil changing in there. I do have a map I was going to show you. You want to pass these out here, and here, just kind of pass them along. If you have to share there, you might have to share a little bit. Why don't you pass those down? Keep one.
They're all the same.
This is a map, South Dakota. It's the water holding capacity maps. And it's color coded, and a nice bright green there is the highest, what they would consider it can hold the most water in what is called the 80-inch zone there. And so the profile at 80 inches, you have to remember that as you go out west, it doesn't seem to have the water holding capacity, but remember there might not be anywhere near 80 inches out there, so you have to keep that in mind. So the soils out there might not be that bad at all. They might be very good soils, they're just not that deep. But if you take a look at Lincoln County there, which is that nice green spot just northeast of here, and you can see why some of those crops over in that area, even though we're getting on to 5 inches below normal, they're still hanging on to what I would call fair to good crops in there. So it's given them some time on those things. And again, okay, we got the maps, but I think you can drive down the road and kind of see what the water holding capacity is on some of these soils. So the differences out here now could be soils, certainly rainfall, of course, soils. Another thing I wanted to talk about a little bit is connected to soils is we have a retired county agent, an ag agent down in Bonham County, and Bonham right now and Yankton counties, they're probably about, as far as row crops in the state of South Dakota, they're done. There's a lot of land has been chopped already. It's in bunkers. So when he was talking, though, about this is getting on to 6 weeks ago, he was already saying, boy, we're starting to really suffer down here. But the main thing he was seeing is no-till, minimum till, and then a good black ground conventional till, and how the differences, it was starting to sort out that way. The no-till was going to buy him, he thought at that time, a little time. It turned out to be about 2-3 weeks if they'd gotten rain in that time, you would have had still a good crop, whereas the others are already down and they were getting rated lower. And so there is something to be looking at. Some of the people need to be maybe looking at the amount of residue on the soil in situations like this. We learn a lot in these kind of conditions. Another thing that I think is maybe not as connected to soil that I see out in the area is it's really a tribute to producers, because if you look out there and you consider that this all started, you're going to see in Bruce's talk when this all started last year. This is we're in kind of it's been quite a few months now of low moisture. It's really amazing that there's even any green out in some of these fields. It's really amazing that these crops are holding on. And I think if you take maybe the tillage, I think there's a lot to say about genetics. There's some corns out there that are showing up a little bit more than not. Just the genetics and the ability to take up fertility and hang on to it. We've got corn out here now. If you go up here and drive into Beersford, there's some chopped fields there, and they had to leave their check strips for the insurance, and just take a look at those if you go up there, and they're curved over. They're not breaking off. They're not kinked. There's no disease in them. They're just so dry that they're just starting to wilt over because there's nothing to hold them up anymore in the wind. It's amazing to me that those hybrids, the practices, cultural practices, and everything that's going on. So it really is a tribute to all the agriculture industry and the producers to be able to have something hang on, so that actually if we got some rain real soon here, we'd get some fair crops in some areas. So I guess that's what I had to talk about today, and again, as consultants and agronomists and producers, it's a kind of a sad story out here right now, but it is a time to learn as much as you possibly can, because when everything is perfect, it's hard to learn a whole lot because everything is good. But now we start seeing some mistakes and some things that are going on. So it's a good time to make a lot of notes and a lot of mental notes of how things are going. So I guess I'll hand it back over to Bruce and we can get going.
The first thing we're going to do is a soil texture exercise. How many are think they're pretty good at soil textures? Raise your hand. How many think they could learn a little bit maybe? There we go. Anyway, I'm going to go through the soil textures right up here, and I'll have you spend about 10 minutes going through all the soil textures yourself. You've got two unknowns at the end, so you got to estimate what the answers are to those last two. So the first one, I'll kind of cater to this camera guy a little bit on this time. This is a sand texture, and there's like 94% sand in the soil. There's about 5% clay and about 1% silt. So the soil doesn't hold together very well at all. This is taken up in like Hecla area. So most of the sand is a fine sand. Second we'll look at is the Motley fine. This has got about 75% sand, about 20% clay, and then the rest is silt. So here you can see it'll start to hold together just a little bit, but not very much. When you feel it with your fingers, you can really feel the sand. The third one we're going to look at is the medium texture. And this here has got about 46% sand and about 19% clay, and then the rest is silt. So you can start to make a little short ribbon out of it, but not very much. So this is the loam on the lower end of the clay content. Fourth we're going to look at is the Marley fine or silty clay loam, and this has got about 12% sand, about 33% silt, about 55% silt, and about 12% sand. So it's got very little sand. So now we can start to make a nice ribbon out of it. This is a kind of a typical surface soil in this part of the state. When you move west of the Vermilion River, then that loam is the most typical texture until you get about to the last row of counties before you get to the Missouri River. And then I got two that you got to figure these two out yourself. So you can call quits on the camera and just have everybody go through and check those 4 textures out and then estimate what those last 2 are, and then we'll talk about the high water, highest water possible. I like that. I really appreciate you coming down.
Pick this up West River.
No, that's right here on this farm. Yeah, both those are on this farm.
I had some West River, I was pulling off 9-inch ribbons.
Yeah, the West River is a lot heavier than this. So between those two, they
Can I shade capacity 44, 45?
you bet. So this one here was a silty clay loam. It would come from the B horizon up in the hill up there. So it's got about 32 or 33% sand, about 50-some% silt, and then sand is about 10% sand. And just down the lower part was this one here. And it's got these both got about the same percent of clay, but this one here feels a lot more clay because the silt, helps makes it feel smooth, whatever. And there's nothing to make this feel smooth because the silt content of this one is pretty low. This probably got about 33% clay and about 35% sand. So if you're out West River, there's a lot of those soils out there. The pure shale soils got up to 60% clay, usually less than 5% sand, and a little bit of silt. So that kind of answers that. So is that a useful thing, doing a little texture exercise? So one of the more important things as far as available water, because the silt loams and silty clay loams hold about 2/10 of an inch of water per inch of soil. And by the time you get to the sandy soil, it may be 0.04 or maybe even less, the amount of water it'll hold per inch of soil. So there's a big variety. Silk loam and silty clay loam are the best by far. How's that? So next one we're going to talk about, has everybody got the handout yet?
Did everybody get a hand?
The groundwater response to precipitation. And Summit, it's got about 12 different sites. That was about 4 or 5 years ago. And so I had this feeling, and so in the spring of 2010, this is like in March, about the 10th of March, I was out there when the snow was trying to melt, trying to put in these water studies. So I put one water study in at Iroquois, and I put one in at up by Volga, and then those actually I did a little earlier, and then if we put one in a little bit earlier, in 2009, we put it at the weather station in Brookings. That's the one we're going to talk about first, the one on the end. Then I put one also at Hazel also. This is where we talk about this, and it'll be the one at the weather station at Brookings. And if you look, we'll look and we'll show that 2010 was a record wet year. So we'd have an opportunity on a record wet year to look at some very rare saturation events in the soil, some that people would say that they're not possible, let's say. 2011 continued on with 2010, had a wet spring, but then the summer turned dry. And then the monitoring that we did was at the weather station, so we had all the instrumentation at the same location. We're going to look at these 2 years, what happened these 2 years, and note that these 2 years are not normal, so nobody should construe them of being the common thing. They're an anomaly of nature, let's say. So then the next page you look at has the picture of where the automated weather station is located, and it's right across from the seed lab. The new seed lab, it's on the agronomy farm. So it's on the top of a hill. If you look at back where our pit was, that's getting close to the top of the hill, but it was almost to the top of the hill on a slope somewhat similar to what we're looking back there, a 1% slope or less. And then if you look at the lineup of the weather station, we got all the pieces there that we need. We have the evaporation pan, So they keep track of how much water would evaporate from a water surface. We had the rain gauge, so we knew how much it rained. They checked it at 8 o'clock every morning. We had my little well, which was at 9 feet in the ground, and they checked that every morning after they checked the rain gauge. Plus they got the wind direction, wind speed, that sort of thing. So we got all the pieces we need. And I'm impressed that this is, if you do a water study, you should do it at the automated weather station. That's the way to do it. Get daily data. So the way I constructed my well, I had a 10-foot PVC pipe. I slotted the bottom 3 feet with a hacksaw. I wrapped some tree fabric around it so that the soil material wouldn't go back in the hole. Pushed her in the hole, put a sand pack the first 3 feet or so, and then bentonite it up to the top. So these water tables I'm talking about are not anomalies. The water had to go through the soil, go through these slots 7 foot down, and come back up in the well to be noticed. Some people would say that can't happen very fast, but I'll guarantee the water, the movement in these soils is a lot faster than what a lot of people think. Most of it happens within a few hours. So then the soil we're going to look at, it's a Vienna soil. So it's got 10 to 20 inches of loess, wind-blown silt over glacial till. It's almost, you see the pit we looked at up on the hill here has got 20 to 40 inches there. It had 30-some inches of silt over glacial till. So the soil here is somewhat similar. Just that's got more silt than this one does, but they're both got glacial till underneath of them. Turn to the next page. So we're looking at those features of soils like we looked at there. We had the rusty features. We had one at 38 inches, and we had the gray features at 44 inches, which are really similar to what we found up on the hill. So you could say these soils are almost the same as far as expecting saturation in your soil. Then the next page, you're going to see a lot of charts like this on these for the rest of the talk. This is the one at Brookings. They started collecting precip data in 1894. So we've got lots and lots of years of precipitation data. And you have to note, for the 20s and 30s here were very dry. So if you look at, say, specifically, let's look at the 30s. So the 30s averaged about, let's say, 15 or 16 inches of precip over the 30s. And say 16 inches, where would that be? Hey, that's like wall. So if you looked at the land here, say at Brookings or down here even, the climate would be similar to what it is normally in wall during the 30s. So it's a very extreme condition. In my charts, I never explained that, but the aqua one in the middle is the average precip over that whole climate period. And then the red line at the top would be the 1 standard deviation above normal. So you'd say the high normal, and then that other line, the purplish or whatever color it is at the bottom, is the low normal. So in some way you'd say even low normal for 10 years like it was in the 30s give you a great drought. Then looking on, 50s, 60s, 70s were somewhat hanging around that normal line, and since about 1980 or 82 we've been above the normal most of the years, let's say. And you see I put some dash lines there. I got a blue dash line. If we'd had 60 years of data instead of that 130 or whatever years of data, we'd be 1.5 inches higher on the average precip. Or if it was just the last 30 years, we'd be 3 inches more than the precip for the long climate period. So I'd say that the last 30 years was not normal climate. It's higher than normal precipitation. And I had a little note up here that if you look at these 2010, the jaggy line, that's each year's precip. In 2010, there's nothing that compares with it anywhere back in history. It's way higher than any other year. And we estimate it's at least 3 standard deviations above normal, possibly even more than that. 2005 had almost 32 inches. 1995 had about that also, though they were also, if you think about that, where our normal was like 22 inches and we had 10 inches above normal some of those years, or 20 inches above normal in 2010. It's a big deal. Turning to the next page, there's the black line on it, the solid black line. That would be the cumulative normal precipitation at Brookings for the last 30 years. And so it turned out to be about 23 inches, let's say, on the last 30 years. The top line we're looking at is the actual cumulative precipitation at Brookings in 2010. and it turned out to be 40 inches. So if you look at the lines below it, we got the green dashed line, which is if you grew alfalfa there, the alfalfa would use all the water. How many remember a wonderful alfalfa year in 2010, right? Everybody could keep harvesting their alfalfa all the way to frost. If you had corn, it only used about 20 inches of precipitation, so we had like twice as much precipitation as we needed. So if everybody looks, the corn was yellow that year, the yields were poor in those lower landscape positions, basically because we had way too much rain. 40 inches of rain would be like what they get, say, in Maine or something like that. So if you think even eastern Iowa, they're thinking, you might have 30, 35 inches in eastern Iowa, so it's even more rain than what they normally get. And turn to the next page was the 2011 cumulative precip. So that black line is the same line we had before, but the red line, you can see it was hanging above. Also remember, in 2010, remember what the corn harvest was like? It was terrible. People couldn't get their corn harvested. It was always all moldy and that kind of thing. It was very terrible, terrible quality of grain. In 2011, we continued on from that. In the spring, we were wet above normal all the way until we get into August. And then the rain shut off. And if you look at the end, we had normal precip for 2011. But it just made up because it was abnormally wet in the spring and abnormally wet in the summer. So if you had alfalfa, you got the dashed line on the alfalfa. Remember, the last crop was nothing. So the alfalfa petered out at the end of the year. Corn crop, we had good corn crops. And remember, hey, can you ever remember a nicer harvest than 2011? There wasn't a single day that combines had to be out of the field because of wetness. So because of that, they got combine done early, and so they did a lot of recreational tillage after that. So we had a lot more tillage in 2011 than what we've had for many, many years. And then the bean crop was also good. You can see that didn't use all the precip. So if you kind of think of a worst case scenario on growing crops, if you say you grew wheat one year, and the wheat would be all done using their moisture by the middle of June, and you go all the way through the next year, you plant your soybeans, they start growing, and the soybeans use hardly any water before the middle of June. So you go a whole year without using water. And that's one of the things that causes our salinity of soil that we'll be talking about here at our next stop. But for this, let's go to the next page. And these are the precip events, the bottom, the blue lines on the bottom with the green dots. Those are the precipitation events for 2010. And we had 6 precipitation events that were more than 2 inches. And the top, the black line with the red dots, that's the soil moisture at the weather station at Brookings, which I remember was almost on the top of the hill, fairly flat landscape, almost on top of the hill. And they weren't doing a very good job reading the water for a while, but then they started to get, it was a little bit more important that they'd better do a better job. And so after about the end of June, the water come within an inch of the surface. The end of June, it jagged along. In July early, it was about 4 inches. In late July, about 1 inch again. And then in September, the water was at the surface or even 1 inch above the surface for 3 days. So when the observer went out one day, the water was on top of the surface. They had sloshed through the water on this hilltop to get to their weather station. So they called it 1 inch above the surface. You remember that flood we had in September the 23rd of 2010? That was caused because the soil was completely full of water. It wouldn't take anymore and it run off. Trivia question for you. Let's say your water is at 30 inches, let's say, and you get 1 inch of rain. How high would it raise the water in the soil? So let's say it rained before, we had, say, 2 days to drain the water out of the soil, and you get another 1 inch of rain. How much would it raise the water? Anybody want to guess?
3 to 4 inches.
I thought it was about 5 inches. That's what my estimate before we did it. But it turned out to be about 10 inches on these average soils like these we have here. So your water's at 30 inches, you get a rain, it goes up to 20 inches, you get another inch of rain, it's up to 10 inches, you get another inch of rain, it's up. So if you have those 3 inches of rain, you'll bring it right to the surface in grass. So if you're in cropland, it's going to be even worse. The cropland will be even worse because you don't use all the water as fast as the grass does. That was the thing I really learned on this project. The next page is 2011. So if you look at the events in 2011, we only had one 2-inch rainfall event in 2011. We had one that was about inch and 3/4, something like that, and the rest are all small rainfall events. But we had a lot of them. And so the last of May, we brought the water within 2 inches of the surface. And then again, from the several events in the, about the 20th of June, we brought our water within about 2 inches of the surface again. And then after 1st of August, we had no rain, and the water dropped precipitously in the hole the rest of the year. So it got by the November 20th or something like that, it had dropped down to over 107 inches, and then we had to put another well, and it dropped it down to about 130 inches before it started coming back up again. That was somewhat amazing to me, how it went down almost in a linear fashion until it got so deeply. Most of this had been for transpiration also. So then when the winter hit, then it kind of flattened out. So you notice here on the top we had 15 inches of pan evaporation between October 1st and October 19th. So it's a lot of evaporation. And say that for the scientific folks, how many people feel you're kind of scientific? Kind of, at least. How's that? Well, scientists think, well, you got to have some replications. That if you just do it one spot, it could be some anomaly or something like that. So you'd want to have some replications to prove that it was true. So I actually had some replications. They weren't right at Brookings, but I had a replication at Volga, which is about 7 miles from there. And they had a Ponce soil, which is a different soil, similar to the soil on your hilltop again, except the glacial till was about 10 inches deeper. And then turn the page. And also I had at Iroquois, which is probably about 65 miles away from Brookings, I had a Sodic soil, which is our state soil, glacial till all the way to the surface. And you think the soils are about the same? Turn the next page and we'll see. So the next page I have the chart that has its daily readings at Brookings, are the ones with the red dots and the black lines. And then the green squares, that's the Ponce soil at Volga. And the purple ones are the Sodic soil at Iroquois. And to me, the answers are all about the same. If you're not really picky about it, and I can actually explain why some of them are different. Like the green dots are higher at Volga than at Brookings because there's more snowpack in the winter there. The grasses were taller, there's more snowpack. In the summer, when these others were dropping, it was hanging up a little bit longer at Iroquois because they had more rain at Iroquois than they had at Huron during that summer. So I can explain almost all the differences why they're slightly different. So essentially, all the answers are all the same for all these different soils. And I guess what I want to take home on this is when you have this dramatic wet year, the 1 in 100 to 1 in 1,000 years, that the water on these types of soils, the heavier soils, the glacial till soils, the silted drift soils, and many others, are going to be right to the surface. It doesn't happen very often, so if you on those, say if you're doing a house base or something like that, keep them above the gray redox features, but then plan is going to be those years that you're going to have to pump your basement for a while. Is there any questions? So that is kind of what I want to talk about on that one. For my discussion on the last deal, remember it was a record year. 2011 was also wet, turned into a dry period. So we had a little subsoil left to start our 2012. And you can kind of see what happened. If our subsoil would have been full when we started this year, our crop outlook would be a lot better than it is today. Anybody have any questions? Thank you very much so far. And then next thing we're going to do is we're going to look at the other pit, the saline soil pit. Anyway, why don't you just put your camera here? There's a bunch of little crystals here. You can see they'll shine in the sun. And those are gypsum crystals. So there's lots and lots of gypsum crystals down that 3 to 4 foot level in the soil. And before we walk down the pit too, you see now before we're in a high landscape position, and now we're in a low landscape position. And so actually it's even lower behind us a little bit, so we're kind of on the edge of a low landscape position. And so this would be an area that, you know, when it was wet, it'd become saturated a lot easier. The water would rush through here when you had heavy rains. Hey, let's go down the pit and check it out. When you get a chance, get a close up of these little white spots down here.
Okay.
That's something that's kind of important. Hey, thanks for coming down in the pit. And a lot of times people don't come down, but I'm really happy you did. So here you can see that there's a little bit of SDSU research has happened here. If you look at the soil here, it's not quite normal. If you look at this side too, that can't do it, I guess. But anyway, the soil should just be dark down to about this deep. But what happened is Greg Carlson had a project where they deep plowed it. There's that deep plow sitting up in the yard. So you can see here is one plow width, and here's the next one right here. So they deep plowed it to almost 2 feet. And so this is just the mixing zone, and here's where the furrow was at the edge of the plow. So you see we got 2 different soils. There's a new history lesson to be learned here. There was one history lesson up there, different history lesson here. And so here now we can see when we look at there's all these little white spots in the soil. And I'm not a lab type, but I got friends that are, like say Ron Gelderman, let's say, and he says that the white spots are dominantly calcium chloride, calcium sulfate, magnesium chloride, magnesium sulfate. And plus we have some calcium carbonate also. So here we look at the lime. Lime in the soil, this is the 10% hydrochloric acid again. And it fizzes really nice here. Probably 15 to 20% of the soil is lime there. Probably 25 to 30% there. And maybe 10% down on the bottom. Is it gonna fizz at the top? How many say yes? How many say no? At least somebody committed. They're wrong though, it fizzes. So this is the Davison soil is the name of the soil. And naturally we got the area right behind us is a little bit lower, so it wicks the salts or whatever around. So naturally this soil had a lot of calcium carbonate in it. But before 1980, I can guarantee this to you because I've been working this area for a long time. I did the soil mapping in Turner County, and there was only a couple small areas out in crop fields that were saline. They were salty like this is right now. And so almost all of this has happened since 1985, let's say, where these soils have become saline. How many can cite that the saline areas are getting bigger? Most people say yes. And that's exactly what's happened. So originally, this calcium carbonate has always been here for thousands of years. This gypsum has been here for thousands of years. But this more soluble salt that's up here on the top now used to be down deeper than the gypsum. So we had these year after year wet conditions. The air was become saturated, and then we had poor crops, let's say, on the ground. A lot of the water left the surface from evaporation rather than transpiration. So it brought this water up from the bottom and deposited the salts near the surface. And I'm estimating I was going to have my meter and stuff, but my meter didn't work. But I would guess the electroconductivity at the surface is probably at least 8. But by the time we get to the bottom, it was probably maybe 4. So we got our highest concentration of the salts are in the top 2 feet of the soil here. And that didn't used to be true. If we'd have gone back before 1980, the salinity up here would have been less than 2 back in 1980 at this particular site. So I got a history lesson that's moving, so our history keeps changing. So what's going to happen next? So if they put a tile, let's say they put a tile here, say you put it down here at 4 feet, let's say, so then these salts are going to start moving back through the soil again over a period of years. Right on top of the tile, it'll probably happen in the first year or two, and then it'll move out from there to between the tiles. In this particular one, I don't think I'll have a problem with, we talked about the sodium problem. I don't believe this soil here has a sodium problem at all. So it'll work, the tile will work here just fine, and over a period of years, the yields will start to increase. The salts will move down within a period of a few years, and they'll have some wonderful crops down here. Anybody have any questions about that?
pH of the soil, like.
I would guess the pH up here is probably around 7.4.
Really?
7.4 to 7.8 probably.
So like 30 years ago, it would have been.
It would have been on the order of 6.5 to 7.2 or something like that at the surface. So, yep.
They don't lime these fields.
No, it's not necessary. No, the only fields you need lime in South Dakota are the ones that are a little bit on the sandy side. There's a few of in the older formations here that might need a little liming where the pH is getting down a little bit low. If you look in the last, say in Minnehaha County, we did the soil survey in 1955, and we come back and did it again. We went to the same locations, and on the hillside locations, most of the pHs dropped down one group. So if it was, say it was 6 before, it would go into the 5.5, or if it was 7 before, it would go to about 6 or something like that. So they all dropped dramatically, say in that 50 years, whatever.
So they're liming.
Some of them are, yeah. Most of them have lime down there, so in some cases we need to, but that's not the dominant thing in South Dakota yet. So anybody have any other comments or questions? I really enjoy the feedback and stuff.
If you're using a Varus machine right now, for example, to move toward precision agriculture
Yep.
at variable rate, you might want to do that if the weather patterns continue to be very much in flux.
Mm-hmm.
You might want to do that again in another 10 years instead of, well, that's the way it'll be.
Yep, I agree with that. And Eugene Preston did a detailed soil survey map down here about 10 or 15 years ago, and he had points that it was a grid survey, and so he recorded each grid point here how deep the salts were. So that's another thing, that a lot of these salts are at the surface now, but they were deeper even 10 to 15 years ago. And this is already bad here 10 to 15 years ago, but it's all got salt all the way from here to the road, and that wasn't that salty back when Eugene did his grid work. So I would suggest for the SDSU research people, go back and study that, do your Varus thing now, and then if you're going to tile it, then go through the Varus after a year or two, every year or two for a while, and just to see what happens.
Bruce.
Hmm?
Gypsum.
Yeah, I showed him already.
You did it.
Yep.
Just played it out.
Here's a nice, you can just pass it around, you can see it glistens in the sun where that gypsum is.
It's like
So on the areas of clay pan soil, which this isn't, so I don't want to get people confused, but on the clay pan soils, we might suggest that you do a soil test before you tile drain those to see if putting gypsum on might be a useful thing. Anybody else have anything? So now you've got two big history books you've studied, and so as crop consultants, you'll see other areas, and you should be able to think that there's a history book that's out in every field, or several history books in the field, that you can study those and learn something about what's happened in the past, and what the potential for crop production is, and what you might need to do to help it out. How's that? So now we're going to go look at 1,000 years of climate history. That's what we're going to do back in the tent now. Why did the salts get here? And it's partly because of that climate history. We're gonna take a look at some of those. So I said I made the talk 1,000 years of climate history, but we're actually going to talk about 12,000 years of climate history. So we're going to even go more than 1,000. But you don't want to be sounding too smug or anything like that. You can do that, but you can, when you get done, you can say, does that make sense or not? You can judge me if it makes sense to you. So on the first page here, we just tell them what we're going to do. We're going to look at the measured precipitation data from Brookings here in Pierre for the last 100 to 130 years, whatever they have. We're going to look at some natural climate history at the Wabi Lakes chain. We're going to look at some other natural climate data, tree ring studies, lake sediment studies. And I got some other things that are mixed in too that you'll find interesting. The next page just shows how my charts are set up. We've already gone through that. So you can turn on to the next chart. And the first chart's Brookings. We've already looked at that one. Just to say, remember the 30s were dry, 20s and 30s were dry, and these were really wet years. So let's turn on to Huron. So if you go to Huron, the 20s weren't quite as dry compared to the 30s. So the Brookings had been, already suffering from some drought, and Huron, the 30s were really dry. And if you look at that, was about 15 inches for many of those years, 15, 14 inches. And so if you think of an area that's about 14 or 15 inches, you can think about Edgemont, South Dakota, about 14 inches of rainfall. So that's what Huron kind of looked like after these 10 years of drought, let's say. And then again, just looking at the same kind of things we looked at, the dashed lines, the normals, raise about an inch. If you use 60 years of climate history, and it raises about 3 inches when you have the last 30 years of climate history. So it's almost equally above normal as it is at Brookings. Third chart then is Pierre. And it starts the average there. Instead of starting higher, it starts about, what, 17.5 inches is the normal at Pierre. So it always starts a little bit drier. The 20s were not as bad as Brookings in the, at Pierre, and the 30s were dry. And it averaged only about, say, 13 inches, 12 inches. So you think about some of that sagebrush country in eastern Wyoming, that's probably about what Pierre looked like at that time through the 30s as far as the climate. And it was kind of average through the 40s, 50s, 60s. 70s was real variable. I was out at Pierre during some real dry years. And then after the 80s, it's been above normal most of the time, except we had those 3 really dry years that brought the normal down. But other than that, it was above normal most all the time. And here's the next page, the food for thought. During the decade of the 30s, all but 4 lakes in South Dakota were dry. Picker Lake, Enemy Swim Lake, Lake Cochrane, there's one other and I don't know what it is. This is about 4 to 5 inches over a decade or decade and a half period will make all our lakes in South Dakota dry. And then during the 90s, we went the opposite way. We went to 4 to 5 inches above normal for the decade. And that's what's caused our lakes to be increasing in size. So actually since 1990, the Wabi Lakes chain has been raising many of the years, let's say. And we're going to talk about that in just a little bit. So it doesn't, you think about how much rain it takes to dry our lakes up, 4 to 5 inches in 10 or 15 years. How much to make our lakes overflow, 4 to 5 inches, 10 or 15 years. That's all it takes. It's not very much. Anybody have any comments on that? When I first figured it out, it was surprising. I thought it took more than that, but it doesn't take very much.
Bruce, okay, we're sitting here now.
Oh. I'm going to biff it here.
It's dry this year, we're coming off of a wet one, and then last August it started drying up. How long will it take to get some of these measures down? I mean, if we have a year like this, does this change much? Well, the lakes, like if you have a lake like, say, Bitter Lake, Wabi Lake, if you have a little drier than normal, it can drop about 2 feet a year. The lake level can drop about 2 feet a year. So if you have a lake that's already 10 feet deep, in 5 years, you could dry it up. If you have one that's 30 feet deep, it might take 15 years to dry it up. Something like that. So this year could take things down a little bit, but since we were so far up, it probably won't show up too much unless we've had a lot of evaporation, so the
2 feet can account for a lot of area, though.
Yeah, like a Bitter Lake too. That might take thousands of acres. So, yep, that's a good question. So what we're gonna look at the Wabi chain of lakes. You can turn to the next page after that. Anyway, Dave Greenlee did a lot of work. He's got, they got all the Lancet images they've been taking, and he used the Lancet images since 1974. So look at the first page, it's got the blue, just shows where the lakes are located. So if you look at the lake that's way on the top, the long, narrow lake, that's Picker Lake. It's really a deep lake. Then you go south of that's Enemy Swim, another very deep lake. And then go to the west, there's a couple different lakes there, but just say Wabi Lake is that larger lake to the central west. The one looks like a peanut, that one is Rush Lake. And back before 85, when I went up there, was mostly it's a cattail slough. And then to the east of that is Blue Dog Lake, which is a nice lake just north of Wabi. And then this particular picture that I'm looking at is the one that's kind of bluish looking. That's Bitter Lake. So probably the blue is looking at all the salt in the lake. It wasn't very deep. So on the left side, it just shows how deep all the lakes are. So enemy swim is about 27 feet deep and bitter is about 3 feet deep. And so what I like you to do is we'll just kind of page through these a little bit, and when we get to about 1992, 1993, things are going to happen, the dramatic changes are going to happen, so just page through your through this handout, and you can just see that the Bitter Lake goes up and down a little bit. 84, it was almost dry.
You can see the color.
85, a couple feet. 86.
Starts changing now.
Yep.
Like 78. And Wabi and everything, just a couple feet really changed.
Yeah. Say then by the time we get, we'll page on to 92. And so in 92, Bitter Lake was about 3 feet and Wabi Lake was about 10 feet. Go to 93. And now Bitter Lake started growing dramatically. So it's up to maybe 8 feet and Wabi is up to 17 feet or 18 feet. 95, well, Bitter's really gone up now. 13 feet, Wabi is 20 feet. 96. Bitter Lake is 14 feet, Wabi is 23, let's say. 97, ooh, it really went up that year. So Bitter is 18 feet, and Wabi is 25 feet. 1998, Bitter Lake is almost 20 feet, and then the Wabi is almost as deep as the enemy swim at that time. So then 1999, 22 feet and 28 feet about. So we'll pass the next page and we'll go to the page that got the yellow on it. So you got a page that got yellow on it. So that's when the study ended that Dave Greenlee did. And so 2009 is the yellow, and so they used the digital elevation model to predict what might happen in the future. So they were trying to predict what happened under these different climate regimes. So we'll go one more page. This is what they predicted could happen in 2007. And so if you look at all the colors in the map that aren't yellow, it'll be the orange and the red and stuff. That's all that those lakes have increased in size after 1999. And actually this is what it looked like in 2011. So if you take the 2011, this is exactly what it looked like. So they're like 4 years behind, but that's not bad. And the next one, this is one of my pieces here. If you look at Bitter Lake, it's got all those little colors, the yellow, the orange, the red. Those are terraces that Wayne Bachman and the others up there mapped along Bitter Lake back when they mapped the soils back in the early 80s. And in 2011, all those old beaches are now covered with water. So this is my thousands of years climate prediction, is that the water has never been higher in Bitter Lake as it was in 2011. It's as high as it's ever been, let's say. Then you turn the page. And this one here is the 2015, which is the outlet elevation. We probably won't make it by then. But if you look at this area, the Bitter Lake is tremendously increasing in size. So if you look at the 1990 to the outlet elevation, it's probably 3 times the land area it would cover. Here's a trivia question. In 1985, Lake Ponce was the biggest lake. By 1987, in South Dakota, by 1987, Lake Thompson was the largest lake. By 1995, Wabi Lake was the largest lake in the state. And if this happens by this, then Bitter Lake will be the largest lake in the state. So it's kind of interesting how you can change that. With other states, they don't have issues like that, but ours can change like that. So, do you think this is ever going to happen? You don't know, but I can tell you this. It's never happened in the last 12,500 years. If you go from where the outlet would be right here, this southernmost red spot, all there is at that end is some pothole wetlands. So if the water ever started flowing out of there, it would form a channel in a very short time, within hours or days. And there would be a channel going through there, and there's no channel there. So we have never outletted Bitter Lake in the last 12,500 years. So there's my long-term climate deal. So moving on to the next page, we have a tree ring study. This is by Carter Johnson. He did it about the same time, 1998, 1999. And you pass the first page, you go to the chart. And so what they did is they looked for old trees that are growing out there. And so people thought, well, there's a lot of old trees in CT Hollow, but there was not one tree that was over 100 years old. So in order to find these old trees, there was an island in Wabi Lake. That's where they found most of these old trees, almost all oak trees. And so they had, if you look at the axis on the left, the right, there were 16 trees that were from 100 years old, let's say. And then some of them were older than that. So they only had one tree that matched the Fort Sisseton, when Fort Sisseton was built. So they had one tree that matched. Oh, darn it. Let's get rid of these guys. Turn the guys off here. That looks pretty bad, don't it? I had some Washington people out one time and my phone rang. That didn't look too good. So anyway, in the Fort Sisseton, there was like 4 trees they used in the Fort Sisseton, and they got back into about 1670 as far as the time frame. So if you look at the climate, back in the 1720s, there was a great wet period, but not as great as what we got now. It was followed by a great drought immediately, and then there was a few minor wet and dry periods, and they got number 4 was a fairly wet period, followed by the great drought of the 20s and 30s. And now we've been on the wet side ever since 1950 looking at this. So maybe we've been doing good on a long period doing it this way. And we're missing 10 years of history here too. At the 2010 is missing off this chart. So who's to guess what's happened next? I don't try to predict the future, but if you look at the past, we go back and forth. The next one we have then is we have Devil's Lake. The thick one is the Devil's Lake water. So that's about 150 miles north of Wabi Lake, and then the narrow line is the Wabi tree rings. And so you can see that they fit reasonably well. I think being 150 miles away, the climate could be enough different that it wouldn't match as well. So I don't get too excited about that one. And turn to the next page is the the Devil's Lake water. Back in 1830, it was 1441 feet, and it's been dropping ever since 1830 until it reached a low in the late 1930s, and it's been going up generally ever since then. So it reached the 1830 mark at about 1995, and then it's been raising. So if you look at the Devil's Lake, it hasn't been any higher. If you look at compare, see if South Dakota was like Devil's Lake, our wet period is wetter than it's been for 150 years, let's say. And Devil's Lake has a natural history that it's run over before, unlike Bitter Lake. So it's got 6 or 8 feet left to run over yet. So, and turn to the next page, we have some other natural data. So what they did is they dug 1,000 feet, took a core 1,000 feet. Not 1,000 feet, but 1,000 years deep into Spring Lake, which is just south of Wabi Lake. And what they did is they tested the calcium-magnesium ratio they're called ostracods, they're like an oyster clam. And they looked in the drier years that have more magnesium, the wet years that have more calcium. And they just looked at the relationship. And they also did the same for strontium versus calcium, which ended up about the same. So this chart in the middle, it's got the same year as the tree ring study, and if you look at it, it's the same thing. So then you have to see, can you believe what happened back to 1,000 years? We've been going from drought to deluge back and forth, repeatedly during that period of time. Food for thought again. Overall, our climate in the last 30 years, or even longer, has been wetter than average. This year after year, above normal precipitation has raised the level of the lakes and closed basins to heights not seen since settlement or much longer. Many state and federal highways have been raised 1 or more times to bring the driving surface above water. If this is my prediction here, this was not anything. If the precipitation would be equally amount low rather than high, brome grass and Kentucky bluegrass would grow in most of our named lakes in South Dakota. How's that for a talk? Anybody have any thoughts about climate or anything that we talked about? You're a quiet bunch. I can see you're taking it in though, at least.
So wouldn't really be global warming that's causing the increased rain?
I don't know about that. It's been happening for thousands of years. So,
global warming is a natural occurrence. It's just that we've sped it up a lot.
yeah, it's,
What my take is on it. I mean, that's a net. We could look over the course of our, the Earth's existence, and
Yeah.
we've had like six ice ages, I think, is what it is. So,
yeah.
but the rate at which we are warming up our oceans, I mean, the whole climate overall, every continent, is just at an increased rate. So,
Yeah, we'll have to see what happens in the future to see how it pans out, I guess.
Well, they were showing all the
So-
glaciers up in Greenland that are melting,
Hmm.
breaking off. Is that normal?
It's happened before, because one of the islands by Greenland, it had become, it come out of the ice, and so they were going to name it, and then they went back to 1200, and they found out that the Vikings had named it already. So it's happened back and forth. So take it for what it's worth. I'm not into that, I guess.
Bruce, is that the same island that they found that there had been houses and barns and things that the ice had covered up?
Yeah, I don't know about that one. So we're going to talk about the water table differences due to cropping choices. This would be in 2010, 2011 again. And there's a lot you can do, to change your water table based on your cropping choices. And the worst choice you can have is either straight small grain, or you can have small grain soybeans, let's say. So if you have let's say you go to the small grain soybeans, you have the small grain, it doesn't use any water after the 15th of June. You go all the year around, you plant your soybeans, the soybeans doesn't use any water till the 15th of June. And so you go a whole year, say if we rain 25 inches at Beersford, you haven't used 25 inches of water, hasn't been used. And so what I'd like to see, and I'm seeing my North Dakota folks say something about it, is after winter wheat, this is we'll get into this some more, after winter wheat or any small grain crop, we should plant something there to use our water up as much as we can, especially if you got some saline issues. So we'll get started on this one though. We're talking about a different soil now. It's called the Stickney soil. And we'll kind of get into this deal that Larry was talking about earlier. So we've got, this would be considered to be a clay pan soil. And you see, if you look at the picture that's got the grass on it, you can see that there's a lot of variety in a short distance. A lot of these clay pans have little tiny areas of the better clay pans and the worst clay pans within a very short distance, or even non-clay pans. And we'll turn to the next one that's got just the soil profile on it. So this would be the Stickney soil. And if you look at the top is black and you get down about to where the 1 is on the foot, there's a gray layer there that goes down to it's maybe 4 or 5 inches thick. And then there's a really black clay layer from there down to about 1.5 feet. And that's the clay pan part. So we'll go that there's, just to keep it simple, non-scientific, all that, there's three different kinds of clay pans. There's the really bad ones, and those have the clay pan that's within 2 or 3 inches. And there's the typical ones, which have the clay pan within, say, 6 to 10 inches. And then there's the ones like Stickney is the better ones, where the clay pan is like moving towards a good soil, let's say. And so if you look at the columns on the really bad clay pans, they're usually with 2 or 3 inches, and their columns may be 1 inch or 2 inches or 3 inches. Some of them can be up to 1.5 feet in diameter. When you see them, a lot of times they're kind of 6-sided, and they got a gray cap on them. And the roots go around between the columns, and the few of them try to go through the column, but it doesn't work that well. And in the typical ones, we had the columns at 6 to 10 inches about, and still those columns are still hard yet. When you dig them out, they're hard to break up, and the roots still go beside them. But by the time you get to the ones like the Stickney soil, you try to break it up, and where the columns were, they break into little blocks. They're like 1/4 to 1/2 inch blocks. And so the soil is much better. It's still got some issues with it, but it's a much better soil. So moving on to the next. So remember we talked about the Hudic soil in that last talk, the state soil. So this one doesn't have a clay pan. So you can see it looks quite a bit different than Stickney. It doesn't have the clay pan soil, but as I look at you, as you'll see later in the talk, it doesn't make much difference. It's still the same answer. So we got the next chart is the year and climate. We've already looked at that, so we can skip that one. And the second one we'll look at then is the monthly climate. So the annual climate's only so good, so I'd recommend if people start working with climate, they should look at least at monthly climate. As you can see, the dash line on the top is the most they've ever received in a month. So say for January, they've never had more than 3 inches per month. In February, they've never had 4 inches per month. This is total precip, including snow. But by the time you get to June, there was a year that had about 11.5 inches. The maximum in July, August, September is a little over 6 inches, and from then on down. And the normal though is the aqua line, and then we got the 1 standard deviation above and below normal for the precip. The dash line on the bottom is the lowest ever. So most months are 0, except for May and June are the only months that here and have never received any rain. On to the next. The next one's more interesting for the people that are all, trying to get a little woozy. So here's the 6 wettest years at Huron. So you can see we caught that year with the high June rain. That's the red dash line. It's 1914. Nobody here remembers that one. It must have been quite an event. And then the next year after that was 1962, and there's a few of us here that remember that. How many of us remember 1962? They're sleeping, aren't they? But then all the other wet years, so 4 out of the 6 wet years, all the people here could remember those other years because they're more recent. And I want you to look at the dark black line. That was the 2010 one, and we were way above normal, like at least 2 standard deviations, let's say, above normal in June and July, and again at least 1 in September. So it was a very wet year. If you look underneath, there's that blue dotted line. Underneath that was 1993, a carbon copy in 2010. And then some other years to look at is the green line, which is 1995. In the spring, it was wet above normal every month in the spring. And then, see what 2011 was just a little above normal, and then towards the end it dropped down to almost nothing. So that's what 2011 was a normal year. And moving on to the cumulative precipitation. So before we looked at the cumulative precipitation at Brookings, so that's the red line, and the cumulative precipitation is here, and is the green line. And then the normal cumulative is the Brookings is the black line, and purple is the Huron is the. So you can see Huron wasn't near as wet in 2010 as Brookings was, but in 2011 they were all about the same. Huron and Brookings were about the same in 2011. That'd be the second part of the chart. Then here's the gutsy part. This is the part I want you to remember something about. It's not on the test though. I asked a different question on the test. This is what I should ask on the test, this gutsy stuff right here. So based on your cropping, what could happen with your water table? So as it turned out, I have all these different cropping scenarios that I had water data on. So the first one's the blue one, and that was corn in 2010 and beans in 2011. The corn was putrid looking. It was yellow all season. It had just little nubbins on it. Maybe only had a ear on that Stickney. Maybe it was only about this long. It was terrible all year long. It yields was 40 bush lift that on the Stickney soil. And you can see during the summer, for more than a week, the water was at the surface in June, and it was at the surface in the end of July, and it was almost at the surface in September. In 2001, in the spring, it was at the surface for a couple weeks in May, and again went to the surface again about the end of June. So you could say the water was at the surface two times for a week and 3 other times for a short period of time. So if you had salts in your soil, like the Stickney does have, it would help bring your salts to the surface. Then we'll look at the red line, and that one was the one when I went out to do the study, and I was hoping to find grass. Well, it was a cornfield at the time, so it had just been broken up for grass for 2 years. And actually, they didn't get it planted that year, so the red line for 2010 was prevented planting. And then the red line in 2011 was winter wheat. So if you look at the prevented planting, it wasn't much different than if it was in corn, because the corn didn't do much of anything. But in 2011, the wheat pulled the water way down in, May and June, so it brought the water down. If it was in grass, that's the pinkish purplish colored line. And also, if you look at the Hudak, that's the black line, and see that the pinkish line and the black line, they're the same. Again, they're the same. Under grass, in 2010, the water never made the surface, so all the water that left the surface was from transpiration, not evaporation. But by 2011, it was too much for it, and the water was at the surface, even in grass, for a week or more, and that started going down. But the one that really excites me then is the green line. The first year we didn't think about it, but we said, well, what if we had alfalfa there instead? And so in 2010, where we started in the fall, it was December, I think I put it in, the water was at about 15 feet. And in 2011, it come up briefly to about 30 inches, then it went back down. And then by, August, it was down to 15 feet again. So the college people told us over the years that alfalfa would go down about 12 feet and take out water, but I can tell you it'll go out down to 15 feet and take out water. So let's say you got a salinity issue, and if I had if I had a spot that was really salty, I'd plant like tall wheatgrass or something, grass that would grow there. And then around the outside, I would plant a perimeter of alfalfa around it to try to bring that water table down, and actually the water table will suck into that grass area somewhat too. And then I would harvest my grass at least twice a year if I could, and I'd harvest the alfalfa at the regular schedule that you'd harvest your other alfalfa. And then when you had your rains, then the water's going to soak into the soil and carry that salt down through the soil. And I think this will do a lot to help a lot of folks out. I guess the thing that bothers me a lot is a lot of people on the government program, they plant their crop, they got these salty areas, they don't do anything with them except control the weeds. So all the water that leaves the ground is through evaporation. So it brings the salt to surface, the wind blows and blows the salt. You can see the salt blowing in the wind. That's terrible. If I had land like that, I would forget about the government program. I would plant my grass in the salted plot. I'd plant the alfalfa around the outside where the grass won't grow, and I'd hope for the best. Anybody have any comments about that? Anybody from North Dakota or anybody would like to make a comment about that, or anybody had some experience? And one thing I'd like to see SDSU do, I'd like to see them test all the alfalfas for salinity, all the ones that exist now, and then maybe work on a alfalfa that'll take even more salt than the ones that exist. Give something for the SDSU researchers to do. And hey, you've been a good group, and definitely enjoyed talking with you, and I hope that you picked up a thing or two, and may I picked up a thing or two from you too.